Welcome to today's lecture. Myself, Assistant Professor Tukur Gupta from Ajay Kumar Garg Engineering College, Ghaziabad. The subject that I am covering in my lecture series is Microprocessor, KCS 403. Today, in this lecture, we will talk about the 8085 microprocessor. In my earlier lectures, I have already covered the basics related to any of the microprocessor. So now onwards, we will talk about the microprocessor 8085 in particular. So today, we will talk about the salient features of 8085 and the internal architecture. 8085 is 8-bit microprocessor. By saying 8-bit microprocessor, we mean that all the arithmetic and logic operations can be performed on the 8 bits at a time. It is manufactured using NMOS technology. There is 16-bit address bus and hence can address up to how many memory locations? 2 raised to power 16. That is 65536 bytes or 64 kilobytes. So when the address bus is of 16-bit, what do we mean by saying this? There is an address bus. It will carry the addresses of certain memory locations. Since it can carry 16-bit of content and it can carry that content is in the form of 1 and 0. So how many combinations can be there? 2 raised to power 16. So it can carry 2 raised to power 16, these many combinations. And what it is carrying? It is carrying the address of the memory locations. So basically, how many memory locations it can address? 2 raised to power 16. So this is how we get this. And the 16-bit address bus is A0 to A15. Here the lower order address bus is multiplexed. What do we mean by multiplexing? That this bus can be used either as the data bus or as the address bus at different points of time. The data bus is a group of 8 lines, that is D0 to D7. It supports external interrupt request. 16-bit program counter is there. What is the role of program counter? It always holds the address of the memory location of the next instruction to be executed. So what is the role of program counter? It always holds the memory address of the next instruction to be executed. Stack pointer. This is the 16-bit stack pointer. It always holds the address of the top of the stack. What is a stack? A stack is the temporary memory space to store the variables temporarily, to store the data temporarily. 6 8-bit general purpose register arranged in pairs. That is, these are 8-bit registers B, C, D, E, H, L. These are all 8-bit registers. But when we want to use them as the 16-bit registers, they can be paired. But these pairs cannot change. B and C can be paired together. D and E can be paired together, and H and L can be paired together. It requires a signal plus 5 power supply and operates at 3.2 MHz single phase clock. It is enclosed with 40 pins dual inline package, that is the DIP package. This is the complete internal architecture of 8085. Here we can see 8-bit internal data bus, which is connected to almost all the modules. This is the interrupt control module, which is having INTR, RST 5.5, 6.5, 7.5 trap. These are all the hardware interrupts. Yes. This INTA. What is INTA? INTA is interrupt acknowledgement pin. Now, this is the serial input output control module, which is having these 2 pins, serial input data and serial output data. And this module is used for the serial transmission of data. In this module, we can see the ALU units. arithmetic and logical unit. With this, there is accumulator, there is temporary register, there are flag flip-flops, that is the flag register is there. Here the instruction register is there, it is used to hold the instruction. Instruction decoder and machine cycle encoder. This is for execution part, for decoding and executing of instructions. This is the register array. Here the 8-bit registers are there. 16-bit 2 registers, that is the stack pointer and program counter. Incrementer and decrementer address latch. This is used to automatically increment or decrement the pointers, that is the memory location of the instructions. Now, in this timing and control unit, there are the power supply signals. There are the crystal oscillator connecting signals that is used to provide the frequency, that is the clock frequency to the circuit. Here the clock out signal is there, ready signal. We'll talk about these signals in detail. Control signals, status signals, DMA, that is the direct memory access signals. There are two signals, there are two pins available for the DMA operations, that is the hold and HLDA. So hold is an input pin and HLDA is the output pin because it is the acknowledgement pin. Reset in and reset out are used to reset the processor and the peripheral devices respectively. Here is the address buffer and data address, lower order address buffer and higher order address buffer. Here the address and the data bus is shown. So when we talk about the registers, there are the 6 general purpose registers, that is B, C, D, E, H, L. Program counter and stack pointer, these are the special purpose registers, that is the 16-bit registers. These registers can also be used as 16-bit registers for the general purpose, but in pairs, that is B can be paired with C, D with E and H with L. Here the instruction registers are also included under special purpose registers. Temporary registers are W and Z, and these are not available to the users for use. These are internally used by the microprocessor for ALU operations. So there are 6 general purpose registers. They can be combined as register pairs. HL can be used for the data pointer or the memory pointer, that is M. It means whatever contents are stored in the HL register pair, they will be acting as the memory location. So it is used as the data pointer or the memory pointer. Registers are programmable, that is you can load, that is the LDA is the instruction to load the accumulator. Similarly, there are the move instructions, move A, comma B, that is you will be copying the data from B to A. So in this way, these registers are programmable. In any of the register, the paired register can be divided into 2, that is the lower order register and the higher order register. When we talk about the temporary registers, so there are 2 units, that is the accumulator and temporary data register for ALU operations. Suppose you want to add the B with the accumulator. So what will happen? First B is transferred to temporary register and then it is added with A. So in this way, this instruction is executed. Similarly, when we are using exchange or the call, so what is this exchange performing? It will exchange the contents of HL and DE register pair. So what will happen? First DE contents are transferred to the temporary registers, then HL will be, and then it is exchanged with the HL. So in this way, the exchange operation is performed using temporary registers. Special purpose registers, A can be included in this category. It is used in arithmetic logical operations, in load operations, store operations, as well as in the input-output operations. Instruction registers are the registers which are used in the fetching and the executing of the instructions. Special purpose registers Under special purpose registers, flag register is another one. Carry, parity, auxiliary carry, 0 and sign. These 5 flags are available with 8085. This flag register, or we can say that these 5 flags of this register indicate the status of the various ALU operations. So what is the significance of S? After the execution of an arithmetic operation, if the bit 7 of the result is 1 during the signed operation, if the bit 7 is 1, then the sign flag is set, otherwise reset. Similarly, if we are talking about Z denotes the 0 flag. So if after the ALU operation the contents of the accumulator are 0, then this flag is set, otherwise reset. Auxiliary carry. Auxiliary carry, this bit is set when the carry is generated from the bit number 3 to bit number 4. Suppose this is your register, that is the accumulator. So if the carry is generated, from bit number 3 to bit number 4, then this auxiliary carry bit is set, otherwise reset. When we talk about the parity bit, it is used to detect the single bit error in the transmission. So this is set when the result has even number of ones. So that is if the parity is even, this parity flag is set. Otherwise, if the number of ones in the result is odd, then parity flag is reset. When we talk about the carry flag, carry is set when the result generates a carry or the borrow is obtained in the subtraction operation. So this carry flag is set when the result gives us a carry or generates a carry. Otherwise, carry is reset. So these 5 flags are considered when going through the ALU operations or when executing any ALU operation. Suppose we are adding these two numbers. This is the instruction add B. What this instruction will do, it will add the contents of B with A. So when we are adding ED with A8, so this is how the result is obtained. It will give you 95H as the result. It will go into accumulator. And during the operation, we can see here the carry is generated. Here the carry is generated at this point from the bit number 3, and also carry is generated from this point also from the bit number 7. So the auxiliary carry and carry both are set. Parity 1, 2, 3 and 4. There are 4 number of ones. This carry is not counted. There are 4 ones in the result. So there is even parity. So the parity flag will be set. The result is not 0. So the 0 flag is reset. And since this MSB is 1, so the sign bit is set. So in this way, after any of the ALU operation, we can judge its status and we can check all the status, that is the flag bits in the flag register. Now the program counter, it acts as the pointer to the next instruction, depends upon the nature of instruction, that is it is of 3 or 1 or the 2 bytes. PC automatically increments to point to the next memory during the execution of the present instruction. In call or jump, the PC changes to the address of subprogram. So whenever the call instruction is executed or jump is executed, what will happen? So when we are currently in the main program, suppose we are at this place, this is 2002. Next instruction is at 2003. Suppose here we come across the call instruction, call at some address. What will happen? When we are at this instruction, that is 2002, the PC at that point holds which address? 2003. Yes. But after executing the call instruction, we have to go to which address? To this address, which is given here. But to go to this address must be loaded into PC. So where will it go? It will be saved to the stack this address to where we have to jump, this will be loaded into PC and the execution will start from this address automatically. So in this way, program counter is used to hold the address of the next memory location. The stack is reserved area of the memory and it works at the in the fashion of last in first out. After every stack operation, stack pointer points to the next available location of the stack. So during every operation in the stack, whether it is pop or the push operation, stack pointer is updated. When we consider the ALU, that is arithmetic and logic unit, addition and subtraction operations are there. To perform the logical operations and or not, compare, rotation, these are all logical operations. Arithmetic, that is instruction register and decoder. The processor first fetches the opcode of the instruction from the memory. This is the first and foremost step during execution of any instruction. So first of all, opcode is fetched from the memory. That is the opcode fetch machine cycle is executed. And then it stores the opcode in the instruction register. It is then sent to the instruction decoder. So instruction register and instruction decoder are very essential during the first cycle, during the first machine cycle, that is the opcode fetch machine cycle. The instruction decoder decodes the instruction in it and accordingly gives the result for further processing depending upon the nature of instruction. So in this way, instruction decoder and instruction register both are used in storing the instructions and then decoding it and executing it consequently. When we talk about the address buffer and address or data buffer, so we are talking about 8-bit unidirectional buffer. The address bits are always sent from the microprocessor unit to peripheral devices and not reverse, used to drive the external higher order address bus. And when we talk about the data and the address buffer, so data buffer is bidirectional. The data bits are sent from the microprocessor to peripheral devices as well as from the peripheral devices to the microprocessor. So this address buffer is 16-bit. This is wrong. This is 16-bit address. Yes, the lower order address bus buffer, address bus and the data bus both are multiplexed. So we can say these are AD0 to AD7. So these are multiplexed address and data bus. Data bus is of 8 bits, address bus is of 16 bits. So here it is used to drive the multiplexed address and data bus, that is lower order address or data bus. These are used. So in this way, address buffer and data buffer are used. So what is bus? It is a shared group of wires used for communication. So here are basically 3 buses, that is the address bus, data bus and control bus. Address bus is used to carry the address from the processor to the memory location. This is unidirectional. So as we have already discussed, the address bus of 8085 is of 16 bits. So it can carry it can carry the 16-bit address of any memory location. So using the 16 bits of address, it can access 2 raised to power 16 memory locations. So that is 64 KB, that is 0000H to FFFFH. So this is the address range of the memory locations available with 8085. That is, it can be accessed using 8085 address bus. Data bus value being communicated is in the range of 00 to FFH. Control bus describes the action on the address and the data buses. So control bus is basically used to carry the various control and status signals being driven during the execution of any operation. So we can have a look at this address bus, data bus, control bus, and with this there are memory, there are input and output devices, and this is our processor. So all these data, address and control bus are very essential for the various operations taking place with our microprocessor. When talking about the incrementer and decrement address latch, it is used to increment or decrement the contents of the program counter or stack pointer as a part of execution instructions related to that. So, incremental and decremental address latch, it is used to update the program counter and stack pointer during the various activities taking place in the processor. When we talk about the interrupt control, so I have already discussed there are 5 hardware interrupts. INTA is the interrupt acknowledgement signal. Serial input output control, that is the serial output line and serial input line. Timing and control circuits signals are control signals, ready, read, write, ALE. S0, S1 input output memory bar. These are the status signals. DMAR, hold and HLDA. Reset signals are reset in and reset out. We will talk about these signals in detail when we will discuss the pin diagram. So this is the pin diagram for 8085. In the further lecture, I will talk about all the signals given in this pin diagram of 8085. Thank you. That's all for the day.